Alright, so now that we're done problem 16, let's take a look at problem 17. And this one states, taking the value of x to the power of x is 0, at 0 to be 1, in other words 0 equals 1, and integrating a series term by term, show that we'll get the integral from 0 to x of x to the power of x dx is equal to summation from n equals 1 to infinity of negative 1 to the power of n minus 1 divided by n to the power of n. Alright, so let's take a look at the solution now. So as in my earlier video on representing functions as power series, we will have to integrate the function x to the power of x by integrating series. We can rewrite, I think it's probably just the same thing as writing it like that, rewrite x to the power of x by using the Maclaurin series for e to the x from the earlier table above, again, which we just went over there, but I'm going to go scroll up to it just in case someone uses the timestamp to problem 17 right away. So let's go all the way up. Alright, so teleporting here, we have e to the x equals to the summation from n equals 0 to infinity of xn over n factorial. In other words, we'll get a 1 plus x divided by 1 factorial plus x squared divided by 2 factorial and so on, where r is equal to infinity. Alright, so teleporting back here, we have e to the x is equal to the summation up to infinity from n equals to 0 of xn over n factorial, which this equals to, well, 1 plus x x squared divided by 2 factorial, etc., plus dot dot dot. It keeps going on and on. Or I'll just add the other 3 just so it looks like it. 3 factorial plus dot 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 and so on. And then I'm going to put r equals to infinity. Alright, so now that we have this, and what we can do is manipulate this x to the x. So the reason we chose this is because it has that power to the power of x. This one is just x to the power of x. So what we'll do is we could rewrite this as e to the ln x. If you recall the natural log rules, those are just the same. That just becomes x. I'm going to multiply this by, then this is to the power of x, where this inside here is just equal to x. And then we could put this x inside, so we get e to the x times ln x, so like that. So we have that, and I'm just going to recap right here. Let's put it here, actually. Recall that e to the y, if e to y is equal to x, then by definition we have ln x equals to y. Yeah, so in other words, if you plug in the y back in here, or I'll just put a recall bubble like this. And then if you put this y back in there, we have e to the ln y equals to x. No, I mean e to the y is e to the ln x. So e to the ln x, not e to the ln y. E to the ln x equals to x, like that. And that is exactly the same thing we have here. So e to the ln x, just x. In this case, e to the ln x, just x. So what we get, is thus, we'll put it like this, thus, or without even thus, I'll just put it like this. Thus we have e to the x, or actually, I'll just put thus. Thus e to the x, or just put the thus like that, and then, so just remove the arrow. Thus, x to the power of x equals to e to the power of ln x. And then we can just throw that inside here. So replace x with x to the ln x. So this equals to the summation up to infinity from n equals 0 of x times ln x. And then this is going to be to the power of n over n factorial. And now if we just multiply that inside, we'll get a summation up to infinity, n equals 0 up to xn. So we'll have x to the power of n times by ln x, that'll be to the power of n, ln x power of n over n factorial. So that is what we have. And now continuing further, so as with power series, and in fact this you could write this as a power series because you have the power there, and yes, this whole thing's as a power there. Yeah, you could rewrite this as a power series. In fact, this e to the x was derived from a Maclaurin series, which is a type of a Taylor series, and that is a power series. So anyways, we can integrate this series term by term. In other words, we could take the integral from 0 to 1 of x to the x dx is equal to then the integral of the inside. Summation from n equals to 0 of every single term. In other words, integral from 0 to 1 of xn ln xn over n factorial. Like this, and then dx. Like that. So integral of every single term. And what I'm going to do now is I'm going to remove this n factorial out of the integral because there's no x inside, because we're integrating in terms of x. So this goes to infinity, n equals to 0, n factorial, 1 over n factorial, times it by, again, integral of x to the n, ln x to the n, dx, integral from 0 to 1. Alright, so now that we have this summation and this giant integral there, or this giant summation with this integral inside, what we can do is we can apply the integration by parts and take a look at this segment separately right here, as per my earlier video. And if you recall integration by parts, how it's derived, basically if you have the derivative of fx times g of x, becomes this fx g prime of x plus g prime plus g of x times f prime of x. Then you integrate that just becomes the integral of this is equal to, of this whole thing is just equal to f of x times g of x. And then integrate inside and then rearrange for this one here, or for this, move this over to the other side, we get this setup over here. And then if you replace this with u and dv, so this could be dv, and this is u, what we get is a uv, and then integral right here of, this is v du, like that. So we can have this set up here. So u dv equals to uv minus v du. And then we have this right here. So there's a product right there. So we could use integration by parts there and to solve this integral and simplify it further. All right. So thus, let's take a look here. So let's look at this integral. So I'm going to put right here, integral from 0 to 1 of x to the n times it by ln x to the n dx. And what I'm going to do is, well, I'm going to look at the one that I want to take the derivative of is this, because this involves a ln x, and we know the derivative of ln x is 1 over x, and the integral is not that simple. So I'm going to actually rearrange this just so it looks a bit better. I'm going to put this in front, ln x n times xn dx. And I'm going to choose this to be u and this to be dv. So it matches u and dv like that. So what we'll do is let u equals to ln x to the power of n. Then this means that du is equal to, well, n, and then ln x, n minus 1, and then times it by the chain rule derivative of ln x is just, it's just 1 over x. So we'll just divide this by x. This whole thing, just divide this by x, like that. And so we let that end, we let dv equals to x and dx, so that the integral of it becomes, well, integral of this just becomes, right here, let's put an arrow, v equals to, integral there is going to be x n. Yeah, actually, instead of just going that, let's go more completeness. I'll just write integral of dv like that, just to show that off. All right, and then the equals to v equals to, and then integral of this is just x. Well, we have to put the, actually, we'll go above. So the integral of xn is xn plus 1 divided by n plus 1. And then it's just the antiderivative. So if you take the derivative, n plus 1 cancels, and subtract 1, you get x to the n. And as always, you're always going to have a constant. So I'm going to have a constant c, and let c equals 0 here. Yeah, let c equal 0, even if it's someone else, it's going to cancel out when we're doing this definite integral there. Yeah, so thus we have, well, v equals 2 xn plus 1 over n plus 1, like that. Yeah, thus, putting this all together, we have, thus the integral from 0 to 1 of ln x n to the power of n, so that's just right here, that's u, times by x to the n dx is equal to, and here I'm going to take a limit, and this is because, well, ln of 0, you can't just plug in ln of 0, that is actually goes to negative infinity. So we're going to have to put a variable as t approaches 0. I'm going to write from the right side. So this plus means approaches 0. So the plus means approaches from the right side. Approaches from right side, from the positive side. But in this case, well, it's positive because it's 0, but from right side. Like that. And this is and now this is going to be of the integral t, so replacing this 0 with a t up to 1 ln x to the power of n x n dx. And again, the reason for this is, well, just recall the function of ln x. So recall that ln x looks like this. This is x, this is y, ln x looks like that. So this is our ln x, and at this point it's at 0 there, but then as here it goes to, right here is approaching negative infinity. So yeah, so this is going towards negative infinity. Let's put an arrow like this. Approaches negative infinity, so hence we're going to go from the right side. It's only defined from the right side. So 0 right. Approach it from the right side as opposed to the left. It does not exist here. It does not exist from the left side. Alright, so it's approaching 0, and it doesn't actually equal 0 there, so we'll just approach it there. Alright, so thus, let's take the limit. So thus what we have is limit as t approaches 0 from the right side of the integral t to 1 of ln x n xn dx is equal to, yeah, it's equal to uv, but since we're doing the definite integral, it's going to be, well, we're going to be writing first ln t approaches 0 from the right side of u, so u is going to be, yeah, ln x, it's still ln x then, so this is u, and this is dv. So this is going to be ln x n to the power of n, that's u. And then dv, remember that one is just x to the n plus 1 over n plus 1. Like that. And yeah, this is our v. So remember that's our v over here, x to the n plus 1 divided by n plus 1, like that. And we're going to go take it up from t, evaluate it from t to 1, like that. And then what we'll do is subtract this by the limit as t approaches 0 plus, and this is going to be, yeah, another integral, so integral from t to 1 of, so t to 1 of, now it's v du, so xn plus 1 over n plus 1, this is again our v, and yeah, so let's put that, that's our v, and then du is going to be, so this is our v, put this a better straight line one more time, and then du is, that's just our times by n ln of x n minus 1 over, this is over, yeah, over x, like that. And then times it by dx there. Well, it's a dx there. And again, this is our, this whole thing, including the dx, is our, this is our du. Alright, so now let's start evaluating this. So that equals 2. So this whole thing is equal to, and let's just put the limit here. T approaches 0 from the right side, and this is going to be, Yeah, this is going to be now evaluated. So put like this, and then ln 1. So put the 1 inside, and then subtract them all. So again, it's going to be ln 1 to the power of n times it by 1 to the power of n plus 1 over n plus 1, and then subtract this by ln t, and then n. This is going to be now t n plus 1 over n plus 1, like that. All right, so then this right here, and now the next setup is, okay, so that's this right here, t, and just, let's see this. And I'm just gonna ignore this limit there. I'm not gonna evaluate the next one. I'm just gonna go subtract this by from 0 to 1. I'm 0 to 1. Because we're not gonna evaluate it right now. We'll just write it as a general form there, or just a simplified form. And actually, before we get to that, I'm gonna put this this n over n plus 1. Take that out of the derivative, the integral, n plus 1. And then integral again from 0 to 1. We're not going to evaluate it, so we'll just leave it like this. When we do evaluate it, we're going to put the limit in, and so on. So then this is going to be xn, this is power of 1, so those just subtract, so that becomes xn. xn, and then ln, yeah, this is going to be, yeah, the next one is going to be just ln, so that's xn, those cancel, and then this is going to be ln xn minus 1 dx. Alright, so now we have this, and I'm going to evaluate this part right here. So when we plug in 1 here, well, ln 1 is 0. We already know this. So this whole thing vanishes, becomes 0, because you're going to have a 0 over, yeah, 0 over any number here is always going to be 0. It's not, the thing is not approaching a limit. This actually equals to 0. Yeah, so then that vanishes to 0, and then we're going to have to subtract by here. So what I'm going to do is look at, look at this limit right here. So we'll put that inside. So what we'll get is limit. So put it right here. So I put a line like this. And I'm going to take this and then do this all separate and take this in. So we're going to get limit, or so this right here, n plus 1. I'm going to take this out, and I'm going to write this as, because it's n plus 1, because it's not part of the limit where t is approaching 0. So just take that one out, and then we're left with limit as t approaches 0 from the right side of this ln t to the power of n times by t n plus 1. Now if we take a look at this limit, so as t is approaching 0 from the right side of this one, again, that goes to negative infinity. So we have a scenario of negative infinity to the power of n. Again, we're going to have an infinity, and times it by this part right here, t to the n plus 1. This is approaching 0. So this is indeterminate. So we want it in the other format, either 0 over 0 or infinity over infinity, to get a, and I'm going to put plus or minus because we're not exactly sure if it's going to be plus or minus because there's power of n there. So we're not, we want it in the form of infinity over infinity or 0 over 0, so we could use L'Hopital's rule as per always. Alright, so now after trying to solve this, the solutions manual just went to the answer. They didn't actually do this, they just said they did it. It took me a while to figure out how they solved this. So first what I'm going to do is note that this right here is equal to, so this part right here is equal to t times n times it by t. Or tn times tn to the power of 1, like that, so you can add those up. I'm going to do that, so then what we could do is, this is equal to, I'll put this equal to 1 over n plus 1 times limit as t approaches 0, as t approaches 0 from the right side. And I'm going to put this t in front. I'm going to, we'll do that actually after. I'm just going to put it like this. I'm going to put this t inside this one here because it's t to the power of n. So that means we could do a t times ln t to the power of n and then times it by t. And now what this part equals to, this whole thing is equal to, I'm going to write this as 1 over n plus 1. So 1 over n plus 1 times limit as t approaches 0 from the right side. Well, in this case, it doesn't matter where you're approaching it for this regular t, but I'm going to just keep it to the right side. So t, like that, that's going to 0, times it by, times this by limit as t approaches 0 from the right side of, and I'm gonna take this ln t times t, but again this is 0 times by infinity, so what I want is I'm gonna put this at the bottom, so I'm gonna do that by ln t over 1 divided by t. This is the same thing, so this still equals to this. It equals same exact thing. And then this is also to the power of n. Yeah, it's all to the power of n, but again, we're taking the limit as t, so it does not matter what n is. And I'm gonna do this like this, times it by, and put this all under this bracket, so all above it. So to the power of n like that. So now, this part right here, yeah, this whole part right here, I'm gonna look at this segment. This is equal with a h on top. In other words, we're doing the L'Hopital's rule here. So this part is equal to limit as t approaches 0 from the right side, and I'll just move this to the bottom. I'll move this lower so we can put an arrow. So put the arrow, or just put an arrow here. And then this whole thing becomes, and now we take the derivative of ln t. So derivative of ln t is just 1 over t, like that. And then the bottom one, that's just equal to t to power -1, and bring that negative down. And then subtract the power will be t to the -2. So in other words, the derivative is going to be t squared, like that. 1 over t squared. 1 over t squared. Yeah, so just like that. 1 over t squared is derivative of 1 over t. So then this cancels with this one. So what we get is equaling 2, and there's a negative t, bring that on top. This just equals to limit as t approaches 0 from the right side is -t, like that. And this just equals to 0. So when you plug in t, it goes to 0. So in other words, this is approaching 0, so then this whole thing equals to 1 over n plus 1, just for completeness, limit as t approaches 0 from the right side. Well, actually, to save time, we don't even need to do that in space. We already have this limit as t approaches 0 of this one. So then this whole thing becomes, I'll just put this whole thing becomes equals to 1 over n plus 1. And then this goes to 0. 0 times it by this right here is 0. 0 and 0 to the power of n, because to be complete, so the power of n there, and which is all just 0. So everything is just 0. So this whole thing becomes 0. So then that means this whole limit, if we scroll up, this whole thing goes to 0. And this is all approach 0. And this is 0, so then all we're left with is just this. This is all we are left with. And just another note here, note this part right here, just because I found it interesting. So if you look at this one, I'm going to put another note. So then now we have it all 0. I'm going to put note also, or just put a note like that, because we don't have another note. So note that, limit as t approaches 0 from the right side of t times ln t. So t times ln t, or this part right here, without that n there. This just equals 2, again using the log rules, t goes to the power of that. So this becomes limit as t approaches 0 from the right side of ln t to the power of t. And remember how we were initially defined that x to the x, remember x to the x at 0, 0 to 0 equals 0, equals 1, equals 1. So in other words, this setup here is approaching, ln 1. It says t over t is defined as 1, so it's approaching ln 1, in other words, it's approaching 0, so this equals to 0. So could have just done it that way, but that was using that definition. I wanted to do the actual L'Hopital's rule setup there, which is all works out fine, so it's pretty amazing stuff. Alright, so let's put it all together. We have thus the limit, or the integral from 0 to 1 of ln x, like this, of n times by x n dx. That is our starting point. Let's go back above here. So this whole thing here, we're not evaluating, so we don't need to add the t. So we can just do integral from 0 to 1 ln x to the power of n times x n dx equals 2, and this whole thing vanishes. This all goes to 0. So 0 minus this setup right there, I'll just put it for completeness, equals 0 minus, and let's just write this down. So n over n plus 1, integral from 0 to 1. So this will become n over n plus 1, integral from 0 to 1. And notice how we have an xn and then a ln x to the power of n plus n minus 1. xn ln of x, let's put a bracket actually, ln x n minus 1, then dx. Alright, so now if we repeat the integration by parts, we can see a pattern. Because notice how this one here, we go from x or ln x to the power of n, and then the n minus, then the n lowers to n minus 1. So we could do this again. So what we'll do is write integral from 0 to 1, and I'm just going to look at this part right here. And just ignore the, well actually I was going to ignore it, but I'm just going to keep that there. So let's just put it all together. So move this xn in front as it was originally. So xn ln x to the power of n dx equals to negative, I'm going to write this negative 1 such like this. I'm going to put negative 1 to the power of 1 times by n, and then n plus 1 like that. And then times this by, this is going to be, yeah, it's a negative 1 like that. Integral from 0 up to 1 there. So yeah, so integral from 0 to 1 of xn. And then I'll put ln x n minus 1 dx. So now what we'll do is, well, I'll just let k equals to n minus 1 here. So if we let that equals to n minus 1, and then what we'll get is, we could just repeat the by parts again. We'll get integral from 0 to 1 of xn, so this part right here, ln x to the power of k, right here, dx. And now we could do by parts again, pretty much the exact same setup we did over here. So we did this, we used by parts, integral from 0 to 1, or limit as t approaches 0 from the right side of t right there. So then we'll have u is this ln x power of n, instead we'll have it to the power of k. And then what we'll get is, yeah, if that's u, then dv is the same here. So we're going to get the same x n plus 1 divided by n plus 1. And then divide this by here, multiply by this, and instead of n, this will be k. And this will be k minus 1 divided by x. And then this x n plus 1 just becomes x to the n again. And we're going to get n plus 1 here, but instead of n, this becomes k. And then this integral is also going to go to, this, when we evaluate this uv, this also goes to 0. It's going to be the exact same thing as before. Instead of n, this will be k. That's the only difference. And k is just n minus 1, so we can manipulate it such that we'll have the exact same integral here. The exact same limit here, use L'Hopital's rule, and etc. And it just solve it. So to save time, because it's literally the exact same thing, I'm going to write equals, and again, but by parts. So we can do by parts again, so you can do that n times actually total. This becomes, put a bracket here, so this becomes negative 1 again, 1, so this will be the exact same thing here, so this k, this n, becomes this right here, this becomes a k there, over the n plus 1 remains, because that n plus 1 is derived from this xn right there, or this xn right here. Yeah, if this is dv, then the integral is x n plus 1 divided by n plus 1. And then there's a cancellation, so that's why there's xn there. And then integral from 0 to 1 of xn times by ln x to the k minus 1 dx. And note here, this k minus 1, that's just, k minus 1 equals to n minus 1 equals to n minus 2. And we could repeat this whole integral by parts, repeat until, or repeat by parts, or instead just write this, repeat n times total until, all the way until we get a scenario such we have ln x of n to the n minus n, which equals to ln x to the 0, which again, anything power of 0 is just equals to 1. So then we don't need to do by parts anymore. So when this is n minus n. So Yes, so if we combine all of these steps, and then let's take this integral right here and then solve it such until we get rid of this ln x variable or ln x term, so we don't need to do by parts anymore, we will get, so thus combining these steps, we get integral from 0 to 1 of xn times ln x n dx is equal to, and we'll see how many times. So we do this a total of n times. So yeah, so notice this n minus 1, this is pretty much a counter, so that's the first. This next one's going to be n minus 2, that's the second, all the way until n minus n, so we do that n times. In other words, we have this negative 1 n times, so we're going to have a negative 1 n times, and then over here is an n, and then this becomes k, which is n minus 1, so what we'll get is n times n minus 1. And notice this one, this is n minus 1. So this is 1 bigger than this one. This k is n minus 1, this is n minus 2. So when this is n minus n, this is n minus n plus 1. So that's 1 more than it. So then this is going to go times it by n minus 2 times dot 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 all the way until n minus n plus 1. And again, we could see that this k, we could just write this as our k1, and this could be our k2 if we keep doing that by brute force. Just if we just keep doing the parts by parts integration, we'll get that. So anyways, this all the way over here, so dot dot dot, and then this is divide this by, well, we have this n plus 1, so this is n plus 1 there, n plus 1 there, and we're gonna have that n times. So it's n plus 1, it's n times. So I'll just put a n plus 1. Yeah, let's put this n plus 1, n times total. And then we're going to take the integral from 0 to 1 of x n times ln x n minus n dx. Where again, this part right here goes to 0, or goes to 1. That's this part right here. That's just our ln 0 right there. So I'll just put this here, ln x 0 equals 1. So that's out of there. So now we can simplify this. This is going to be negative 1 n. And now this n times n minus 1 times n minus 2 all the way to here. That's just n minus n cancels. That's just 1. That's just n factorial. Divide this by n plus 1 n. And now the integral of xn, well, we know that. That's just going to be xn plus 1 over n plus 1. Like that. And we're going to evaluate that from 0 to 1. So what we get is, put this here, negative 1 n times n factorial over n plus 1 to the power of n times it by, and put the 1 inside, we'll have a 1 n plus 1 over n plus 1. Again, 1, it just makes everything 1 there. Well, actually the top is just 1 divided by n plus 1. And then we're going to subtract, put the 0 inside, 0 to the power of n plus 1 over n plus 1. That's just 0. So I'll put it over here. This just equals to negative 1 over n plus 1 power of n times it by 1 over n plus 1 minus 0. And here I just forgot the n factorial. I'll put the n factorial there. So then this all becomes negative 1, and there's a power of n. So negative 1 power of n factorial over, so n plus 1 to power of n, this is going to be n plus 1 power of 1. So n plus 1 to power of n plus 1. Alright, so now this right here, let's put this down here. This is our integral 0 to 1 of xn ln x to the power of n dx. And now I'm just going to bold this like that, or just square it. Alright, so that was just this integral. Now let's go back to what our question was this whole time. So thus, we're going to go back to the integral we're dealing with was integral from 0 to 1 of x to the x dx. And now this was equal to, if we scroll all the way back up, and just to get sight of what we were even asked to do, which was over here. So we were asked to find that integral from 0 to 1 of x to the power of x to the power of x dx is equal to the summation from n equals 1 to infinity of negative 1 to the power of n minus 1 divided by n to the power of n. And then we showed that x to the power of x is equal to this right here, equals to e to the x ln x, which equals to this, and the integral over here. So this is the integral we got up to here so far. So integral, so the summation from n equals 0 to infinity of, so then we'll have 1 divided by n factorial times this integral, which we just finally solved. So let's put that in here. So thus, this equals to the summation. So summation up to infinity from n equals 0 of 1 over n factorial. And then times by our integral 0 to 1 of x to the n ln x to the power of n dx. So now let's plug that inside there. So this equals to, plug in our answer for that. N equals 0. We have a 1 over n factorial. So we get this over here. Negative 1n times by n factorial over n plus 1 to the power of n plus 1. All right, so we get this, and then this cancels with this. And we are left with, we are left with right here, summation, erase this. I'll put this here like this, summation from n equals to 0, fix this again one more time. That's a very good one. Okay, so negative 1n over n plus 1 to the power of n plus 1. Yeah, so notice here, so that if you plug in 0 here, at n equals 0, we get 0 plus 1 to the power of 0 plus 1, and then, at the top is going to be negative 1 to the power of 0. So instead, start at, just to make it like our question, start at n equals 1 instead. N equals 1, so what we'll do is, we will shift this over by 1. So instead of n plus 1, we'll just go with n. So that this is 1, 1, 0, this will just be n minus 1. So I'll just erase that, actually. And instead, I'll just write here. So start at n equals 1, or start at. Just because we don't have to, but the question had it as starting at 1 actually. So if we scroll back to the top, so we got the answer, but the question said specifically make it show that it's from n equals 1 to infinity of negative 1 to the power of n minus 1, and then n to the n. So yeah, that's all we do. We just switch it up so that it's written starting from 1. So that's all they're doing, start at 1. Yeah, so when we do that, what we get is, put this in here, thus we get the integral from 0 to 1 of x to the x dx is equal to summation up to infinity from n equals 0 of negative 1 to the power of n minus 1. So when we start at 1, will be 1 minus 1 is 0, same as n is 0 there. And then over n to the power of n. So that when it's 1, it just becomes 1 over 1, as opposed to when it's 0, it's still going to be 1 over 1. So we're not changing anything. So we just write it like that notation, and this is exactly the same answer we were asked to find.